Okay, let's unpack this. We are diving into what is really the ultimate cosmic speed limit. And this isn't just a number, it's sort of this invisible universal barrier that dictates, well, everything, from your phone signal to how galaxies are structured.
Exactly. And our goal today is to, really get to the bottom of why this constant c is so foundational, why it's always the same, and why physics itself says it's absolutely unbreakable.
And when we say c, we're talking about a very specific number for the speed of light in a vacuum.
A very specific number. It's 299,792,458 meters per second, precisely.
That's a huge number. I think we need to put it into perspective for you.
Yeah, it's hard to grasp.
So imagine this. In just 1 second, a beam of light could circle the entire Earth about 7.5 times.
Wow. Or, think about it closer to home. When NASA sends a signal to the moon,
right,
that signal takes about 1.3 seconds to get there. That little delay, that C in action.
And it took us a surprisingly long time to even figure this out. The first real hint was back in the 17th century with Ole Römer.
He was looking at Jupiter's moons, and he noticed that their eclipses seemed to be off schedule depending on where Earth was in its orbit.
So he figured the light had to be taking time to travel that extra distance.
He established it was finite, yeah. But the next huge leap was James Clerk Maxwell in the 1860s. His equations for electromagnetism just sort of spat out this number.
They demanded that these waves light had to travel at this exact speed.
And then, of course, came Einstein, 1905, special relativity. He took it from being just a speed to being a fundamental principle of the universe.
Yeah, that's the key step.
And it's so important to remember this isn't just for light, for photons. The name c comes from celeritas, the Latin for speed. It's the speed for any particle with zero mass.
Like gluons.
Gluons, hypothetical gravitons. But even more than that, it's the speed limit for information. Nothing, no message, no cause and effect link can beat it.
Okay, and this is where it gets really interesting. Because to understand it, you have to sort of throw out everything you know about how speeds normally work.
Right, our everyday Newtonian intuition.
Exactly. I mean, if I'm on a train going 100 kilometers an hour and I throw a ball forward at 10 to someone on the platform.
It's going 110. You just add them up. Simple.
But with light, that completely breaks down.
Completely. This is the principle of invariance. So let's do that thought experiment. You're in a spaceship, okay, and it's already moving at 90% the speed of light.
So 0.9 c. Moving incredibly fast.
Incredibly fast. And you turn on your headlights. Now, you'd think.
You'd just add them. 1.9 c. You've broken the speed limit.
You'd think. But it doesn't work that way. The person on the ship measures that light beam moving at c. And a stationary observer watching you fly by also measures that same light beam moving at c.
It doesn't change?
It never, ever changes. It's the one absolute constant for every observer everywhere. And that's what makes it the ultimate unbendable rule of the cosmic highway.
So the natural next question has to be, why? I mean, if this rule applies to everything with mass, what's the actual physical mechanism stopping us? Why can't we just build a better engine?
And that takes us right back to Einstein in 1905. It's all about energy and mass. As you push an object that has mass, as you accelerate it, the energy you're pouring into it doesn't just make it go faster. A lot of that energy starts to, well, it increases the object's resistance to being pushed more.
So it's not the mass the object has when it's just sitting there, the rest mass. You're talking about its effective mass. It feels heavier the faster it goes.
Precisely. It gets harder and harder to accelerate. This effect is described by something called the Lorentz factor, gamma.
Okay.
You don't need to know the exact formula, but just know what it does. It's the multiplier that tells you how much this effective mass increases, and as we'll see, how much time slows down.
And what happens to this factor, this gamma, as our speed gets really, really close to set?
Well, the denominator in that formula, it gets closer and closer to zero.
And when you divide by a number that's almost zero,
The result skyrockets. It approaches infinity.
meaning you would need an infinite amount of energy to push an object with mass to the speed of light.
Infinite energy. And since the universe only has a finite amount of energy, it's impossible. Physics itself just says no.
And this isn't just some abstract theory. We actually see this happening in places like CERN at the Large Hadron Collider.
Oh, absolutely. We see it every day. They get protons up to speeds like 0.999999 c, just shy of the limit. And at that speed, those protons are behaving as if they are thousands of times more massive than they are at rest. The math checks out to an incredible precision, something like 10 to the minus 20. We know this is real.
Okay, so the moment you accept this speed limit is real, the consequences for Well, for space and time itself, are just mind-bending.
Yeah, this is where reality starts to feel like science fiction.
Time dilation and length contraction.
The two big ones. They are the unavoidable results of the universe twisting itself to keep cheese constant for everybody. Time dilation just means that moving clocks tick slower.
We can actually see that happening. The example of atmospheric muons is just wild.
That's a perfect example. Yeah, these are particles created way up in the atmosphere. They have a really, really short lifespan.
They should decay before they ever reach the ground.
They absolutely should. But because they're traveling so fast near the speed of light, their internal clock slows down from our perspective.
To say they live long enough to make the journey.
Exactly. Their survival is direct proof that motion slows down time.
And then going hand in hand with that is length contraction.
Right. Space itself has to compensate. So in the direction of motion, space actually shrinks. If you saw a 100-meter spaceship fly past you at 80% the speed of light,
you wouldn't measure it as 100 meters.
No, you'd measure it as being only 60 meters long. And that's not an illusion. It's a real physical compression of space.
This all leads to some very strange personal consequences, which brings up the famous twin paradox.
Which isn't really a paradox so much as just a very strange fact of life in a relativistic universe.
If you leave Earth, travel at these incredible speeds, and then come back, time will have passed differently for you.
Massively differently. Let's use the most extreme example. Say you travel to the Andromeda Galaxy.
2.5 million light years away, so a trip that should take 2.5 million years.
For someone on Earth, yes. But let's say your ship can do 0.9999 C. The time dilation is so extreme that for the crew, the journey might only take, say, 28 years.
So you age 28 years.
You come back, you're a few decades older.
Yeah.
But Earth, and everyone you knew, has aged 2.5 million years.
It's just staggering. It also means you can't have a real-time conversation with anyone far away, that delay to Mars.
It can be anywhere from 3 to 22 minutes, one way, so a conversation is impossible.
And beyond just communication, C is what protects causality, the order of events.
This might be the most important reason it's unbreakable. If you could send a signal faster than light, you could create paradoxes. You could receive a reply before you even sent the message.
The effect could happen before the cause.
And then the entire logical structure of the universe just dissolves.
This also sets the boundary for everything we can ever know, the observable universe.
Exactly. The universe is about 13.8 billion years old, right? So we can only see the light from things that has had 13.8 billion years to reach us.
So when we look at a galaxy that's, say, 10 billion light years away,
we're seeing it as it was 10 billion years ago. We are literally looking into the past. C acts as a cosmic time machine, but it also puts a hard wall on our vision.
So given how strict this limit is, have physicists just accepted it? Or are there, theoretical loopholes, ways around it?
Oh, they've definitely theorized. But we're really on the fringes of physics here. The most famous idea is probably the tachyon.
Right, a particle that always travels faster than light.
That's the idea, proposed by Gerald Feinberg in '67. For a tachyon, C would be its slowest possible speed.
Which is already a huge red flag.
A huge one. And to make the math work, they'd have to have what's called imaginary mass.
I have no idea what that even means in reality.
Nobody does, really. And the biggest problem is that, from our perspective, a tachyon would be traveling backward in time, shattering causality all over again. And, every search for them has come up empty.
Okay, so no tachyons. What about shortcuts through space-time instead of trying to go faster in it?
Now you're talking about wormholes. Or, more formally, Einstein-Rosen bridges.
The idea being you fold space like a piece of paper and just punch a hole through it.
That's the perfect analogy. You're not breaking the local speed limit at all. You're just making the journey incredibly short.
So you could get to Andromeda faster than light would, but without ever actually exceeding C yourself.
Precisely. The problem, the huge catch, is keeping that wormhole stable. To keep it from collapsing instantly, you'd need, something called exotic matter.
Okay, and exotic matter is?
It's stuff with negative energy density. Basically, it would have to have repulsive gravity.
Something that pushes space-time apart instead of pulling it together?
Right, and while it's mathematically possible in general relativity, we have no idea if it exists or if we could ever create enough of it to stabilize a wormhole. So, still purely theoretical.
So what does this all mean then? We started this deep dive thinking of C as this frustrating cosmic speed trap. But the more we look at it, it seems like it's not a limit, it's the architect.
That's a great way to put it. It is the absolute cornerstone of reality. Without C being finite and constant, electromagnetism just wouldn't work.
Atoms wouldn't be stable.
They wouldn't. Electrons would lose energy instantly. And causality, that reliable, predictable chain of events, would be gone.
And it all connects back to that famous equation, E equals mc squared.
That relationship between energy and mass is only meaningful because C is a specific finite value. It holds the whole thing together. It's an elegant, rigid framework for the entire universe.
We can appreciate how necessary it is, even if it does sort of keep us in our own backyard.
For now, anyway.
So I guess we should leave you with a final thought to mull over, right? Based on everything we've talked about, since dictates the structure and history of everything we know, what profound changes to our reality, to energy, to life itself, to the nature of time? What would happen if the speed of light were different? What if it were, say, 10 times faster?
Or maybe more unsettling. What if it were 10 times slower?
Yeah, just think about that.